नमस्कार, सुस्वागतम, अभिनंदन, केम छो, वणकम, आदाबाज, सत श्री अकाल, राधे राधे, खुशामदीद, ए वेरी गुड आफ्टरनून। मैं अनिल भारद्वाज आप सभी का पीआरएल के अमृत व्याख्यान के 92वें एपिसोड में स्वागत करता हूं, अभिनंदन करता हूं। I, Anil Bharadwaj, very warmly welcome all of you to 92nd PRL का अमृत व्याख्यान। This is also the 17th PRL का अमृत व्याख्यान of PRL का अमृत व्याख्यान version 2.0, which started on 30th of January last year, that is 2023, after we completed 75 episodes of PRL का अमृत व्याख्यान। PRL, established in the year 1947 by Dr. Vikram Sarabhai, completed its 75 years in the year 2022. And hence, the PRL Amrit Vyakhyaan is a celebration of the legacy and history of PRL in the field of physics and space sciences. Today, we have yet another very distinguished Vyakhyaan with us, Professor Kathrin Altwegg, who is Emeritus Professor at Department of Space Research and Planetology at University of Bern in Switzerland. And she is delivering the Vyakhyaan on Deciphering the origin and evolution of our solar system from the chemical composition at 67P. 67P is the name of the comet which was visited by Rosetta, and she is going to deliver the talk on that. So we greatly thank and appreciate Kathrin for agreeing to our invitation and to deliver the Vyakhyaan today. I would now request my colleague, Dr. Kinshuk Acharya, to kindly introduce today's Vyakhyaan Karta to the audience at the WebEx panel, as well as those who have joined us live at PRL's YouTube channel. Over to you, Kinshuk.
Yeah. Thank you, Professor Bharadwaj. It is an honor and privilege to introduce our today's speaker, Professor Kathrin Altwegg. She is an Emeritus Professor of the Department of Space Research and Planetology of the University of Bern. Is an internationally renowned scientist in the field of cometary science. Professor Altwegg obtained her doctorate in experimental physics from the University of Basel, Switzerland in 1980, and proceeded to undertake postdoctoral research in the Physics Chemistry Department of University of Technology, Design and Architecture in New York. In 1982, she returned to Switzerland and joined the University of Bern in Space Exploration and Planetology Department. During her tenure at the University of Bern, she served as the director of the Center for Space and Habitability of the university and also led the calibration facility for solar wind and magnetosphere instrumentation and the neutral molecular beam facility of the university. She is popularly known for her work on the Rosetta mission as the project manager and the co-investigator for Rosina instrument on Rosetta. Dr. Altwegg authored over 150 scientific publications in the referred journals, including publications in Nature and Science on the topics related to cometary science, plasma physics, extraterrestrial physics, space science instrumentation, ion optics, physical chemistry, and organic molecular crystals. In addition, she has contributed immensely in the development of the space research program in Switzerland as the scientific secretary and treasurer of the Swiss Commission on Space Research of the Swiss Academy of Science, and as the editor of the Swiss National Report of the COSPER Committee. These are just a few of many. With this brief introduction, I invite Professor Altwegg to deliver the lecture. Professor Altwegg.
Good afternoon, everybody. I will just present my So you see it? It's black.
It is black.
Yeah, not for long. Okay, I'm very happy to talk to you in India. I would have preferred to be there in person, but through WebEx is also okay, of course, and it's much easier to do. I will talk today about this mission, about Rosetta, which you see here, looking at the comet, the small lander Philae, also looking at the comet, and of course, about the comet itself. It's actually a year of celebration for Rosetta because it's exactly 20 years since the launch in 2004 and 10 years since we arrived at the comet in 2014. The launch was foreseen for 13th of January 2003, and the comet, the target comet, was Comet Vyakhyaan. But I don't know how it is in India. At least in Switzerland, 13 is a bad number, so you should never launch on 13th. And so it happened as it had to happen. Months before our launch, an Ariane 5 rocket failed. There was an investigation about the cause, and we were not allowed to launch in January. And the comet Vyakhyaan just didn't wait for us. So we had to look for another comet, and we found it in comet Churyumov-Gerasimenko 67P, which is easier to spell. And we could finally launch just a year later on 2nd of March 2004. That was a perfect launch. We launched in 2004. We had an Earth flyby in 2005, went to Mars, back to Earth, encountered the first asteroid Steins, went back to Earth, and finally encountered the second asteroid, Lutetia, in 2010. We had to do these flybys in order to get enough velocity to join the comet on its orbit. In June 2011, we were far from the sun. The solar panels, 64 square meters, were not enough to really supply the energy necessary to operate the spacecraft. So we had to switch it off. You see here the last heartbeat of Rosetta. And it was in hibernation for 2 years, 7 months, and 11 days. It was a long period, and we didn't know if it would come back after this time because we had to really switch off everything, transceiver and receiver, and it had to wake up all by itself. So on January 20, 2014, we put all our alarm clocks at 10 o'clock and hoped that Rosetta would hear it far, far away from the Earth. And we calculated that we should get the signal at the 6:45 in the evening, latest, and at 6:45 in the evening, there was no signal. So this was actually my longest half hour in my life. The signal appeared at 1919 Central Europe time. The problem was that the computer on Rosetta did a reboot, and that takes half an hour. So, and you see the signal here, and everybody was very, very happy at ESOC, the operation center of ESA, and also in our institute. And with this, we knew that the mission would be a success. Rosetta was a big spacecraft, 3,000 kilograms. It contained, of course, a good camera, OSIRIS. Then our instrument, Rosina, a gas mass spectrometer suit. Then a few instruments to measure the dust, a few to measure a few spectrometers in all wavelengths, a plasma instrument suit, and then the radio experiment and CONSERT, the Comet Nucleus Sounder, which had a receiver and transmitter on the lander and another one on Rosetta itself. And finally, the lander Philae, which again had 9 experiments, altogether 100 kilograms. What was the task of Rosetta? Rosetta is deduced from this stone here, the Rosetta stone, which was found by the troops of Napoleon in Egypt long time ago. And you see here in 3 languages, hieroglyphs, Egyptian, Demonic, and Greek, the same text. So this is the first dictionary on Earth. And this stone, this small stone, it's about 70 centimeters large, was the reason why hieroglyphs, the Egyptian old language, could be deciphered. And ESA thought that the spacecraft Rosetta, by studying a small body, a really small body, 4 kilometers in diameter, would be able to do the same for the origin of the solar system, the Earth, and life by studying this comet. So that's why Rosetta is called Rosetta. And we tried to do that by looking at the chemical composition, mostly the chemical composition of the gas phase in the coma of the comet. So our instrument did not land on the comet, it was in the coma, it measured the sublimating species from the nucleus. And we have a lot of species which we measured, and actually each species has its own tail. So if we look at the comet, we find traces from the interstellar medium through the dark molecular cloud stage to star-forming region, to the protoplanetary nebula stage, and finally to our solar system, and even to the evolution of life. And the material will evolve, of course, starting with the starting conditions, so with the material in the interstellar medium, but then also the chemistry and physical conditions according to the stage we are in. And by studying the comet, you find traces of all of these. 67P, it's a Jupiter family comet. It's, as I said, 4 kilometers, the longest dimension. It had a rotation period of 12.4 hours when we arrived. It was just 12 hours when we crashed. It got slower due to non-gravitational forces. It has an orbital period of 6.5 years and a perihelion distance between Earth and Mars. It has a tilted rotation axis, and the density is 0.5 grams per cubic centimeter, which is very normal for a comet. The porosity is very high, 75%. And so as far as we can say, the comet is more or less homogeneous. And it's dark, it's black, it's very black. What we found is we have 2 pieces. We actually had 2 comets. Churyumov-Gerasimenko is clearly made out of 2 pieces. You can derive that from the layering here. If they would have formed at the same time together, the layering would have a common gravity center, but that's not the case. This piece and this piece are clearly formed separately and then collided very gently in the end. We have 2 hemispheres, or well, the comet looks a little bit like a duck. We have 2 hemiducks, the northern hemisphere and the southern. The northern hemisphere has a long but cold summer. The summer is during aphelion, whereas the south has a short summer, only about 10 months, where the sun is over the south during perihelion. So during perihelion, you lose a lot of mass here, several meters of height, and part of this material is deposited in the north. And that's why you see the fine-grained north here, which is very different from this material in the south, where you have ice and dust mixed, sintered, more or less. We have found features in all sizes, starting from the 4 kilometers of the comet to 100-meter pits here, as you see, then to 2-meter features here. That was during landing of the lander. 10-centimeter features here. You see the feet of the lander, so that's after landing. And then we have from the COSIMA, the dust mass spectrometer, we have microscopic pictures which show you sand, more or less sand in the range of 200 micrometers. And finally, the microscope, the atomic force microscope, which goes to down to 100 nanometer sizes. So these are probably the original interstellar dust grains, which we still find in the comet. So the comet is not a rock. The comet is clearly a mixture between dust and ice. Our instrument, and I talk here mostly about the Rosina DFMS, double focusing mass spectrometer. That's how it looks. It's a classical mass spectrometer. It contains a magnet and an electrostatic field. In the Near-Johnson configuration, 15 kilograms at launch. It measured between 12 mass 12 and 180 Daltons. The ionization of the neutral particles was done by electrons, and the mass resolution is 3000 at mass 28 at the 1% level. This corresponds to roughly 9000 full width half max resolution, which for a space mass spectrometer is unique. It's, I think, the best mass spectrometer ever flown, and there is no other mass spectrometer in space at the moment which has this resolution. It doesn't measure very fast. It measures one integral mass after the other, so it takes quite some time to get the full spectrum. But as we spent 2 years around the comet, we had plenty of time. The comet, we encountered it when it was 3.8 astronomical units from the sun, so quite early. And then we followed the comet very closely to its perihelion and then out again to 3.8 AU post-perihelion. And our instrument got about 2 million mass spectra during this time, and that's why we are still analyzing it. It really takes a long time. The coma densities varied quite a lot. Of course, if you are at 3.8 AU, not too much material is sublimating, but still there is material sublimating. And then it also depends from which side you look at the comet. That's these variations here. You look at the front of the comet, of the duck, or you look at the side of the duck where the area is much bigger. Then you look again at the rear part and at the other side, and that's exactly corresponds to the period with which the comet rotates here. And here we were over the summer hemisphere, at that time the north. Here we were over the winter hemisphere where you have less sublimation. So these coma densities really varied a lot, of course, depending on how far from the comet we were. And here you see one sample mass spectrum from Rosina. It's mass 60 here. We see many different peaks and can really give them names, so we know at least some formula for them. So Rosina, the task of Rosina was really to explore the chemical composition. And from the elemental composition, you gather the temperature of formation of the comet. So the more volatile the species are, the harder they are to condense. and that gives you a hint about the temperature of formation. Isotopic composition, on one hand, tells you something about where this species comes from. I will talk about the noble gases later, and you will see. On the other hand, it will also tell you something about the chemical evolution, especially if you look at deuterated species versus normal species, because then you have this reaction which is temperature dependent, density dependent, and so on. And finally, the molecular composition tells you about the chemistry which was ongoing in the different stages of the material. So gas phase, ion neutral, and gas grain surface chemistry. I will come back to that. It was surprising that when we encountered the comet at 3.8 AU, we already got a lot of different species in our mass spectrometer. And I'm not a chemist, I have to tell you, I'm a physicist, so I always forget the names of the chemistry, but I know animals. And that's why I try to sort our species according to a zoo. And we make a visit to this zoo here. First of all, the zoo is based on water, so the main species in the coma is water. And we were able to measure the deuterium content of this water. And we can, here are the spectra, and we can compare that to molecular clouds. In comet 67P, we have a high D/H value, but that's it's a little bit lower than what we expect in molecular clouds, but of course it's much higher than in the sun. It's about the factor 30 higher than in our sun. And we have also measured the doubly deuterated water, so the D2O. And if you do the D2O to HDO ratio, then you get 1.8%. And that's comparable to what we have in molecular clouds. And if we take this ratio, the D2O to HDO versus the HDO to H2O, this ratio is 17. If we would have material from a thermal equilibrium, this ratio would have to be 0.25. So it's very much disequilibrated material, what we see here. If we compare our D/H values with other comets, then you see we have Hartley 2 and Vyakhyaan, which are almost solar, whereas all the others are above solar, including our 67P, which is here. With this, we can say that the terrestrial water was most likely not brought by comets, because the mean value of all the comets is way above the terrestrial value. We can also look at other species, the deuteration of other species, and you see it's always around 10 to the minus 3, the D/H ratio, independent of the molecule we look at. So that's H2S. In Hale-Bopp, we have HCN, which we cannot do in 67P. Then we have NH3, and then a few others, CH4, the alkanes. So CH4, C2H6, C3H8, they are all very similar to each other. And we also have the carbonaceous chondrites, the ordinary chondrites, which are all generally much higher than we have on Earth. What does it tell us? So water is most probably inherited from the pre-solar cloud and not from down in the solar nebula, because otherwise the D/H should be lower. We have quite a big variability. If you look at this here, in water, which probably means that comets were formed over a large range in solar distances. So probably Vyakhyaan and Hartley 2 were formed closer to the Sun than 67P. There is no real difference between Oort cloud and Jupiter belt comets. The Earth did not get the bulk of its water from comets. I will come back to that. Also, other molecules like the alkanes are probably from a pre-solar origin. And here, what you see here in this plot is methanol, deuterated methanol for pre-stellar cores and low-mass protostars up here, and comet 67P over here. So high-mass protostars are lower. So the methanol is really compatible with what we also measure in low-mass protostar regions here. So that's my zoo. And we start with the butterflies. Butterflies are very volatile. So these are the volatile species: nitrogen, N2, oxygen, O2. And especially the oxygen was a big surprise. We didn't expect that. Oxygen, O2 is very active, reactive, and it should have disappeared long ago, reacting with all kinds of other molecules. We also have, of course, carbon monoxide, carbon dioxide. The presence of these highly volatile species tells us that the comet probably formed at 25 or 30 K. And O2, as I said, is very puzzling. There are 3 mechanisms proposed for the origin of O2. It's first of all an Ellie-Riddle effect through H2O+, which reacts and finally ends up in O2. Then this mutation during sublimation with this reaction here. But that would mean, that would mean we should see a lot of H2O2, which we don't. And the third proposal was radiolysis of water ice. And finally, it has to be a primordial cloud gas phase or gas dust chemistry, which produces the O2. And for this, we can look at the oxygen isotopologues of the molecules. And what you see here is that in the comet, all oxygen 16O to 18O is depleted, so 18O is enriched. And O2, if you look at O2, is more enriched than water. So that tells us that O2 cannot come from water, because otherwise it should have the same oxygen isotopic ratio here. And it also tells you something about the formaldehyde, which you have here, and the methanol. Methanol is actually the only molecule which has a terrestrial or solar isotopic ratio for oxygen. That means methanol does not have the same formation pathway as formaldehyde. So the conclusion from this is the enrichment of the heavy oxygen isotopes in water is compatible with current self-shielding models of the formation region of stars. And the high fractionation in O2 rules out 3 of the 4 proposed mechanisms. So the Ellie-Riddle, the dismutation, and the radiolysis, because that all depends on water and it's not compatible with water. That leaves you just the primordial cloud gas phase or gas dust chemistry. Back to the zoo. What was quite interesting was this here. We have the treasures with a hard crust here. These are refractory elements. Our instrument just measures gas species, not dust. So before Rosetta, we thought that a comet contains simple molecules which have formed in the gas phase, and then there is a refractory part which is made out of magnesium, silicon, iron, and so on. But what we found is silicon, and we found it over the whole mission in our spectra, gas phase silicon. And we also found iron and a few other refractory elements, sodium, calcium, and magnesium. We found them early in the mission, and we found them during perihelion. And absolutely no parent molecules belonging to these refractory species. We looked for all possible parents. There is none. The iron was also seen from ground in many comets. And there was a paper by Bodewitz, which gives you two options how this atomic species, refractory atomic species, could end up in the gas phase. One is you have metal bonded polycyclic aromatic hydrocarbons, which we know we have in a comet, or you have the metal carbonyl. And we looked for the iron carbonyl, and it's not there. It's definitely not there. It should be visible. So the only thing left here is this aromatic hydrocarbon where you have metal or silicon bonded, which then with UV, with sunlight, comes off and is in the gas phase as atomic species. Let's go to the smelly ones, the sulfur. We see a lot of sulfur species. The most recent one, which is not yet published, we see the DMS, the dimethyl sulfide, which was detected in an exoplanet maybe, and people there claimed that's a sure thing of life. We have DMS in the comet and no life, so there is an abiotic way to make the dimethyl sulfide. If we look at the sulfur abundance in comets, then it corresponds to the cosmic abundance. While in the interstellar material, it is known that sulfur is depleted. Sulfur is missing by factor of 10 or 100. We see sulfur in different molecules. We also see these S2, S3, S4, up to S4, we can measure, and we saw it. Probably it goes further up to S8. And this cannot be formed in the solar nebula. So it has to be inherited from the pre-solar cloud. And these are not so volatile as S3, S4, and the following ones. So they are on the grains. And that's probably why you don't see them if you look at interstellar material, because they are not in the gas phase. So you have a bias in observation. We have S2. S2 is very volatile, so you should have it in the gas phase, but it's very easily destroyed by UV. But we have it in the comet. That means it must have survived the formation in the ice, or with other words, the ice was never in the gas phase. It had to survive as ice from when it was formed to when we measured it. Now let's go to the big animals, the giraffes, which are the long carbon chains, the elephants, which are the ring molecules, and the funny animals, the alcohols. And here we have some exotic molecules. These are molecules where I didn't find an animal to associate with. Hydrocarbons, CNHM, we have all over in the coma of 67P. They are really everywhere. On each mass you find them. That's a mass spectrum between 12 and 140. And if you look in detail, because we have a high resolution, then we see different, we see sulfur pairing, we see species which have N and O, we see pure hydrocarbons, C6H10, all over the place. And it's not so easy to then analyze our mass spectra. These are just CNHM with no heteroatoms, so just C1, H2, 3, 4, and so on. And C8 here at the end of the scale. Now, if you want to analyze them, you look at molecules which have this form here, and then you have to know the fragmentation pattern, because we ionize our molecules with electrons, they will fragment into daughter species. So you will still have the parent ion, but also quite a few of the daughter species. If we do that, so we put in ethane, C2H6, then we can fill up our measurements. We can, that's the parent here, the last one. So we can fill this up, and then we get some fragments in all of the others here. We add to the ethane the propane, and then the other alkanes. This still leaves a lot of empty spaces here, so that's not good enough. Then we add alkenes with a double bond, CC double bond, and alkenes with CC triple bonds. So first ethylene, acetylene, propene, and then we fill this up. And still you have a lot of empty spaces here, even if you use all of these. So the next step is then the ring molecules, the cyclohexane, cyclopropene, and so on. So that fills up some more of the empty spaces. And finally, you also need the aromatics. That these are rings with double bonds. And then you can really fill up most of what we measured. Not all of them, as you see, there is still some empty space here, which may come from molecules containing heteroatoms. So just CNHM, we end up with 44 parent molecules. And that's the list we detected. I don't expect that you can remember any of them, but you see we have hexane. The heaviest one is decahydronaphthalene. That's a ring molecule with 2 rings, actually. We have, of course, naphthalene itself. We have indane, but also cyclooctane, and so on. So there is really a long list of CNHMs in this comet. It's clear this solution is not unique, but it's also clear that there are other solutions which might be less likely, but still I have to admit it's not unique. But you need all of these. You need the alkanes, alkenes, the cycloalkenes, and the aromatics. Otherwise, you cannot explain what we measure. You can do the same if you take the CNHMO, so with 1 oxygen, or with down here 2 oxygen. We did that. We have another long list. I just want to point out the furan. The furan, that's this molecule here. It has oxygen here in this ring. And here, it's an aromatic. We have different furans. So the normal furan is this here. Then we have the hydrated with two hydrates here. With two hydrogens. And then we have the tetrahydrofuran, that's this here. So where the double bonds are only single bonds, but you have more hydrogen. And you see, the more hydrated the molecule is, the more abundant it is. So hydrated molecules are in general more abundant than non-hydrated molecules. And that's not only for furan, but for all of them. And then we can look at furan 2-methyl. So this contains a methyl group somewhere. And you have the 2,3-dihydro-4-methyl. And again, they are higher than the pure furan. So molecules which have a side chain, mostly methyl group, they are more abundant than the pure molecule. And that's also true for sulfur-bearing and for nitrogen-bearing molecules. So that's the structures we see in the chroma of 67P. All of them, chains, rings, double rings. And now you can compare that with carbonaceous interstellar dust, and you find similar structures here in this carbonaceous material. And actually, COSIMA, the dust mass spectrometer, has found such carbonaceous grains in 67P. However, if you look at the average composition, in our case, that's the average composition of all species. That's the same for the Murchison meteorite and for COSIMA. You see that the difference is mainly in the number of hydrogens. In our cases, it's 1.5. COSIMA is 1.0, and in the Murchison, it's 0.6. And this means the more hydrated the species are, the more primitive and volatile the species are. So this composition actually resembles mostly the soluble organic matter in meteorite. Another big surprise we had is the ammonium salts. That's how it looks, ammonium chloride, but you can form ammonium salts with any base. It's easily formed from NH3, ammonia, and an acid, from any acid, not base. And the salts have generally a higher sublimation temperature than the individual species, ammonia and the acid. If you sublimate them, they go back to their, mostly back into their original molecule. That's the ratio of H2S versus NH3 over the whole mission. That's 600 days of data. And you see, if you look at the ratio, it's actually more than a factor 100, which it changes over the mission. You also see here these up and downs. That's the hemisphere, which shows you that H2S versus NH3 is not the same over the two hemispheres we are looking at. And this here is the heliocentric distance, so perihelion is somewhere here. But now if we look at the individual species, and we divide it to here by O2, abundance of O2, sulfur by O2, they have the same mass 32, NH3 by OH, that's also the same mass. then what you see are these spikes here. These are now only 50 days, day 440 to 490, and you see these spikes. They last for a few measurements, and one measurement is roughly 40 minutes, so they last between 1 hour and 3 hours. And these are actually dust impacts into the instrument. So we get dust grains directly into our ion source, where they sublimate, because there the temperature is much higher than in the coma of the comet. And what we found is that in this, if we just look at the impact material and the use, what we have in the normal coma, then we see that in these dust grain events, the most abundant species is NH3. The second most abundant species is H2S, whereas water is just 100 here, is less abundant than the others. This really points to ammonium salt. Ammonium salt, mainly hydrosulfide salt, but also we have other acids here. And you see, if I add up all acids versus the ammonia, which is the base, it adds up, it balances. So NH3 in this impact material is mostly in the form of the salt, as are all the acids here. And finally, let's go to the king of the zoo, the lion. It is known that the lion eats zebras. Zebra that smells of horse manure. And so it's ammonia, methylamine, and ethylamine. If you take methylamine or ethylamine and mix it a little bit with butterflies, mainly with carbon dioxide, you get the glycine, the amino acid, which is, of course, a building block of life. And we found the glycine. Another very important building block is, of course, phosphorus. And together with people from the ALMA community, we could really reproduce the story of phosphorus from the supernova, where phosphorus was built by nucleosynthesis. Then it's sputtered from dust in the outflow. It's then converted to pH3 phosphine. But as PO and PN are more stable than pH3, it ends up in PO. We find PO in 67P, and that would be a way to deliver active, reactive phosphorus onto the Earth as a building block for our life. So that's a very nice story, I think. But for this, we have to know if comets actually did bring anything on Earth. We've already saw that it's not the water. But what we can do, we can look at the noble gases in 67P. If we just look at argon, all we can say is that our atmosphere is compatible with a delivery of this argon by comets. This would not really change the D/H ratio because it's not enough water to have an influence here. But we can look at xenon. Xenon is a much more interesting noble gas than argon. Xenon has 9 isotopes, starting at 124 and ending at 136. And depending on the process, it's different stars where the xenon isotopes are formed. So supernova formed the P process, 124, 126, which we actually didn't find in 67P because these are very minor species. Then HEB stars, 128 to 132. And finally, neutron star mergers, where you get the R process, 134, 136. You also get some 128 9 xenon from the decay of 129 iodine. So if we look at the noble gases in the Earth versus the solar value, so it's normalized to solar here, then you see there is a trend here. The heavier the noble gas, the more you have. The same is true for chondrites, but for chondrites it goes on, whereas for the Earth, xenon is missing. This was explained by loss due to mass fractionation. You can correct for this. What you then get is this peak here, which you can ascribe to the decay of 129 iodine. And then you get this curve here. But actually, if we do this fragmentation, mass fractionation correctly, what you find is that you miss 134 and 136 xenon in our Earth's atmosphere. This is not true if you look at the Earth's interior. In the Earth's interior, you have too much of those. So a long time ago, people came up with the notion that there has to be a U xenon, U for Ur, that's German, it's original xenon, which is depleted in the heavy isotopes. But nobody found it until we measured 67P. If you now combine the measurements of 67P, the xenon isotopes, and combine it with the meteoritic xenon in our Earth's interior, then you can reproduce exactly what we have in our atmosphere. So our atmosphere is a mixture between meteoritic xenon, 78% roughly, and 22% cometary xenon. And that would explain the depletion of the heavy xenon isotopes. And from this, you now can find out how much water was delivered. If we assume that 22% of the xenon came from comets, then we end up here at a maximum of 2% water of the terrestrial water, which could be cometary. And of course, this does not change the D over H in our ocean water. However, it's a lot if you look at the organics. So the water is just 10 to the 19 kilograms, but the organics is 10 to the 17, and that's more than today's biomass. Comets may well have something to do with life on Earth. Come to the conclusion, I think mixing in the protosolar nebula was inefficient, otherwise we wouldn't see these different isotopic compositions. All would be solar if the mixing would have been efficient. And the protosolar nebula chemistry in this case was probably not very efficient for comets. We still have a lot of chemistry from pre-solar stages. These prebiotic molecules, including the salts, which also are can help to build life, they really point to a rich pre-solar chemistry. So the nebula chemistry was not very important. We are still evaluating and analyzing data. We see still some more animals on the horizon. We didn't identify them yet, but we are doing that in the next few years. And so please stay tuned. That was 67P, the last perihelion. Very nice picture here. I'm happy that it comes and goes and comes and goes. And every time I see this comet, I think about Rosetta, which is on the surface of the comet and doesn't answer anymore, but I know she's happy up there. And I really would like to acknowledge the first principal investigator of Rosina, Hans Balsiger, who did all the preliminary work, who brought together the team, who brought together the money, and who was my mentor over all this time. Unfortunately, he died in 21. Thank you very much.
Thank you very much, Professor Kathrin. It's a very fascinating story and wonderful set of results from your zoo of cometary molecules as measured by Rosina. I'm sure there will be a lot of questions after this very exciting and inspiring talk. Those of you who would like to ask, please raise your hand or unmute yourself and can ask. I have a few questions, but I'll keep them to the end, I think. Yes, Professor Bharadwaj, please.
Thank you, Kathrin, for a very nice talk and giving an overview of the science results which has come out from Rosetta mission. And could you just again summarize of the major results in terms of whether comet has delivered water to the planet Earth?
No, the comet, if comets delivered water, it was probably less or around 1% of the terrestrial water, which is not much.
Not
so
much.
The water has to come from somewhere else. Don't ask me where, I don't know. Maybe asteroids, but my feeling is a little bit that the Earth may have kept enough water in the interior, which survived and which built today's ocean. You know, the Earth is a very dry place.
Right.
Okay, good. Thank you. Thank you.
So I had one question regarding the zoo, but before, maybe I think I can ask Insuk, please.
Yeah, so a very fascinating talk actually. So it was, so I have maybe a few questions. First is that whatever abundances that you are seeing, so how it is related to the as you can see that the comet is being formed around very low temperature. That is what you have shown, like around 25 Kelvin or something like that, right? So what implications it has in terms of abundances that we see? Because whether it represents the overall reservoir from where the material can be delivered on Earth.
You mean to say the primordial abundance?
Yes, because this comet is formed, as I have seen from your slides, at very low temperature, like 25 Kelvin or so. So this might preserve your precellular organics much better than the comets which may be processed at high temperature.
I didn't get it.
Maybe I think if I might request, I think he wants to ask how much this, we assume that the comets were formed at low temperature. That's what you mentioned in your slide.
Yes.
So they are retaining the imprint of the
interstellar,
protosolar nebula or the interstellar medium.
Yes.
So I think his question is, I might have missed it again.
Now,
but
how representative that can be in terms of overall cometary population?
Yeah, so he wants to know how unique this is or how general this kind of.
Okay, I think it's very general, and that's one of the important results. You know, if comets contain more or less pre-solar material, this is not unique to the Earth.
Right.
Then it's really universal, and if you have exoplanets and you have the same mechanisms probably all over the universe, more or less.
Yeah, and we do see similar composition even with the interstellar comet.
Yes. Okay. But of course, then to really get life from these building blocks, that's another story.
Right. Yeah.
I always emphasize there is no life on the comet. Definitely no life. But it's easier to form life from if you already have some building blocks as if you have to start from atoms.
Right. I can see that Ramakant has raised his hand. He is a noble gas person here in PRO. Yeah.
Good evening. I have one question regarding this noble gas composition. Can we say that this cometary composition, because this is determined for the first time, is representative of the nebular composition?
I don't know. And we have one comet, so statistics is very poor.
Okay.
I admit it. But what we see in comets is that actually they are all quite similar. It's not, there are no Kuiper belt and Oort-Cloud comets, they are very similar in composition. So why should the noble gases not be similar? But it's a poor argument, I admit. We just need more comet missions. You are a spacefaring nation, so go to a comet.
Okay. Just one another query. What about carbon and nitrogen isotope ratios?
Carbon is, as far as we can say, it's like everywhere. However, nitrogen is, of course, a lot enhanced in nitrogen 15. So it's not terrestrial, it's not solar, but and for nitrogen, the interesting thing, it doesn't matter on the molecule. So we have the same isotopic ratios for N2, NH3, and other nitrogen-bearing HCN, whatever.
Okay. Yeah.
And that's something nobody understands, I think.
Yeah, Dr. Deepan, please, you can unmute and ask.
Yeah, thank you very much for this nice and informative talk. Very good result, actually. So I see that you have shown that Bajovsky et al. Result where they have compared the organics using ALMA and in different other bodies. So it is generally shows some kind of heritage with the comet, right? So what about the isotopic ratio? Because if it is the like say heritage, can we expect to see similar isotopic ratio?
We compared the methanol
Yes.
data, and this is compatible with low mass star forming regions. So there we have very similar isotopic ratios for the deuterated species.
No, but for oxygen and nitrogen, that's very like
yeah. I think oxygen is difficult. I don't know about measurements from ALMA, but probably there are.
Yeah, so they show very scattered values.
And nitrogen is very diverse in the universe.
Yes.
You have regions where N15 is enriched, other regions where N15 is depleted, but in the comet it's very much enriched.
Okay. So and another questions, like you said, like if depending on the formation regions of comets, we expect to see different kind of chemical composition of the comets, right? But you also made a statement like that comet, all this composition is forming around 25K. So is this not like little bit contradictory statement? Because if the central star is here, then depending on the distance, there should be some region where this temperature is there. Okay, something 25K or something. But if they are forming in different regions, like say different ice line locations, their composition should be different.
Yeah, that's true for the very volatile. You know, we come to the 25K if we look at how much CO and N2 we have in the comet. For other comets, it may be less or more. I think for Oort-Cloud comets, probably It's more. They have more super volatiles because they kept them. Our comet has already lost some of the very volatile, as far as we can see. So
Okay.
but that doesn't really tell you about formation temperature. But the fact that we still have them points to the, not how much we have, points to a low formation temperature. But I would assume Hartley 2, which has a terrestrial D/H, has probably less N2 than our comet. Just
Okay.
because it did not condense, or not in the same way.
Yeah, one last question. So if we like from ALMA perspective, if we are going to see the disk, okay, so we expect to see the inheritance from the disk and comets. Is that we expect, or there should be some kind of reset chemistry also?
Well, the material of comets is from the very outer disk, I think. So further out than Jupiter, certainly.
Okay.
And that's probably true for all comets, but some comets, we know it from Will 2, also got some dust grains, hot CIAs, which came from the sun. So material was mixing in the protosolar nebula, but that does not affect probably the volatiles too much. It's the dust which is diverse, and not really the volatiles.
Okay, thank you
But
very
we
much.
have to measure more comets. Yeah, you're right.
Yes. Yeah.
Definitely.
Yeah. Okay. Thank you.
Okay. Goldie, you can unmute and ask. I have a question.
Thank you, Kathrin, for the wonderful talk. I have a few questions. One which is regarding a D/H ratio. As you showed that that there is a variation in the D/H, but we also saw that just some comets like 103P and again there is one Oort cloud comet C2014Q. They showed the same close to the V small level. So are we actually deducing our results based on the observations of few comets? And we are saying that comets didn't deliver water to Earth.
No, it's not only the D/H, it's also the xenon.
The xenon. Okay.
You know, if comets would have delivered the water to Earth, our xenon would be different, because then they would have delivered much more xenon to our Earth's atmosphere than what we see.
Okay.
I think we can really base it on both. It cannot be more than about 1%. Otherwise, we have a problem with the xenon. And probably also with the other noble gases, krypton.
Okay, so remember, is there any fractionation effect, like isotopic fractionation happened during the formation of during the formation of our solar system? And then right now what we are saying is actually the effect of that.
Can you repeat?
Ma'am, isotopic fractionation could happen also, which actually affects the D/H ratio and the other ratios.
The D/H, yes, this can change, but not the xenon.
Yeah. No, I think he's asking whether fractionation effects can affect the values.
Fractionation upon sublimation, you mean?
Ma'am, actually,
Which fractionation?
No, ma'am. Actually, what I meant to say is this isotopic fractionation could happen during the formation, like when the solar system was forming. So the materials can.
But then in the solar system, you had a low D/H ratio, 10 to minus 5. That's the solar value.
Yeah.
And if you have chemistry during the solar nebula, then you would lower the D/H. That's for sure.
Right.
Okay.
It goes only one way. You cannot enrich it in D/H You can only lower it in the solar nebula.
Okay. Thank you.
Thank you.
Yeah.
That's probably what happened with Hartley 2. You know, if it was formed further in, then it had more time to do reaction with the H2 in the solar nebula. Isotopic exchange ratio. Isotopic exchange reactions.
All right.
Yes, ma'am.
Yeah, Amit Basu, you can please unmute and ask.
Nice talk. I have two questions basically. First one is, when you say delivery of water or gases from comets or any other planetary objects, do you mean the delivery time is during the accretion or planet building stage, or during the time when the whole planet got its shape, and that was also very early stage?
Can you repeat? I didn't get the first part.
First part is that when this delivery took place, you said gases or water delivered from comets or any other planetary objects. So did you want to mean that this delivery happened during the planet formation stage or after formation?
After formation. After formation, because during the formation of the planet, the Earth was way too hot. If water would fall on the Earth, it would immediately be lost.
Right. No, but
it has to be the heavy bombardment period.
Yeah, but if it is a big planet, then heat escape is not that efficient because there is a cap of say crust, which can
It would still destroy the water. You would get OH probably, and well, the Earth didn't have any water in the beginning, so this water was all lost to the atmosphere and then ionized and lost to space, probably.
Okay. Yeah, but Earth has got a lot of water in the mantle. Okay. And that Earth has formed during that stage, and when the volatiles got accreted. That's why it is in the interior.
Yeah. This I actually don't know, but I always suppose that comet impact happened during the heavy bombardment, as you see from the craters of the moon, on the moon.
Yeah. And second question is, you mentioned that metals are organically connected in comets. So I mean, in some comets, some metals like Mg and other sodium, those are found. So, but comets are very cold, and how metals can even exist there? Say, for example, Mg, magnesium, which must have formed by nucleosynthetic process, right? And we may expect some short-lived radioactive nuclides also in that.
Well, I know about papers which claim that you have nanograins in dark molecular clouds composed of PAHs. And they can absorb metals, probably also silicon, and that's, in my view, what we see at the comet. So if they get warm, they will release the adsorbed species, and then the metal will just be in the gas phase. But I don't know. It's actually, for me, still a little bit a mystery why we see it. And it's well, iron we don't see very much. But silicon we see really during the whole mission.
Okay.
And it's clearly coming from the comet. It's not the instrument or so. It varies with where we are over the hemispheres and so on, and how far we are from the comet. So it's clearly a cometary signature in the coma. And we looked for silicon oxide, silicon carbide, silicon whatever. And there is no parent. It's just silicon, pure silicon.
Okay.
But if you have a good idea, I'm very open to all suggestions.
Okay, thanks, Kathrin.
Thank you.
I think I had just one last question. I think, you know, your zoo of animals, which you mentioned, all the molecules which you're seeing, you have seen them in the gas phase in orbit around the comet. Can you actually trace them down back to the source locations on the comet? And I mean, you do have a lot of spectra, so.
Yeah, we can pin some down to the source.
Mm-hmm.
We did that for the very volatiles, so we know where we have CO2 and water are not correlated, so
Okay.
we now are working on the correlation between the species. And what we have found, and it's already published, is that the very volatiles, the species which are more volatile than water, they are trapped in water ice and trapped in CO2 ice.
Okay.
And
Right.
depending on the species, it's more in water or more in CO2. For
Okay.
example, methane is half and half. Half is in water, half is in CO2 because they correlate
Right. Right.
with water and with CO2. But if you take only water, they don't correlate well. If you take only CO2, they don't correlate well. If you take a linear combination of the two, then you get the perfect correlation.
Okay.
Oxygen, for example, it's almost always in water. 99.2% is in water, 0.8% is in CO2.
Okay.
And we also do a laboratory experiment which confirm if you freeze out water and these highly volatiles, that's what you get. You get the phase for CO2,
Right.
phase for water, and then you trap the individual species.
Okay.
And of course, you get also a phase of pure CO, of pure N2 methane, but probably this comet has already lost these pure phases of the very volatiles.
Okay.
We don't have them anymore. In the lab, you still get them and they disappear at 20K or so.
Okay. Okay. I see.
So
Nice.
that for those species we can say. Now the interesting thing is, for example, methanol. It does not correlate, neither with water, neither with CO2, neither with a combination of the two.
Oh,
It's
okay.
uncorrelated. So the location where methanol comes off is not from the water ice.
Okay. Nice. I see. Interesting.
And that's interesting. We are working currently on that, also for the other organics.
Okay. Okay.
None of them, the alkanes, they correlate very well with CO2. But all the other organics, they don't correlate.
Very interesting.
So
Okay.
they are, yeah, I guess they are on the dust. They are
Most
probably
likely.
a layer on the dust.
Right. Yeah, because that's, I think, one of the sources where you have a lot of stuff happening.
Yeah,
So,
yeah, exactly.
right.
So, but that's an interesting way to go.
Right.
We are
Yeah.
working on that.
Okay. Thank you very much, Kathrin. I think there's a lot of very interesting stuff that we have heard from you today. And I will now hand over my session chair to Vineet for the vote of thanks. Thank you.
Okay, thank you.
Yeah, thank you very much, Professor Sashikiran Ganesh. And so that brings us to the conclusion of a very interesting 90-second episode of PRL Amrut Vyakhyaan. We would first like to thank Professor Kathrin Altwegg for accepting our invitation and giving an excellent talk on the topic of deciphering the origin and evolution of our solar system from the chemical composition of 67P in today's event. Also, we are thankful to Professor Altwegg for answering the audience's questions. Next, I would like to take this opportunity to thank our audiences on both of our platforms, YouTube and WebEx. Next, I express my sincere thanks to the PRL Director, Professor Anil Bhardwaj, Dean PRL, Professor D. Pallam Raju, and Chair of the PRL Amrut Vyakhyaan Committee, Professor Nandita Srivastava, for all their support in organizing this episode of PRL Kamrit Vyakhyaan successfully. I also thank my colleagues in Vyakhyaan Organizing Committee for successfully conducting today's episode of PRL Kamrit Vyakhyaan series. Kindly visit our website and other media platforms to know more about upcoming events being held at PRL, in particular this event, PRL Kamrit Vyakhyaan. And with these words, I propose the closure of today's episode of PRL Kamrit Vyakhyaan. See you next time. Thank you very much.
Goodbye.